In a lot of situations, it really helps us in physics to deal with or to consider conservation of energy. This whole notion that energy is conserved. So maybe I'll give you a little definition here. So we'll say that energy is, well, it's neither created or destroyed. All it does, so I'll say it merely changes form. This is really important. This comes back to the original definition that I gave you about energy, where I said that, if you could just count up the total energy before something happens, then it's going to be the same as the total energy afterwards. Now remember though, there's lots of different types of energy. This is the key thing here. Remember, we've been looking at just a few of them, but there's lots of different types of energy. So when I say that it changes form, something can go from, for example, we have kinetic energy and we have potential. So maybe we can have a situation where something has all potential energy, which means stored, and then all of a sudden it can change and it can give some of its potential energy to make it kinetic. But it turns out the total of potential plus kinetic plus all the other types, the total will remain constant. So it can switch. This energy can go in different forms. So we have kinetic, we have potential, we have chemical, we have electric, we had magnetic. We also had considered thermal. Turns out we have sound energy. I mean, there's so many different types. There is nuclear, there's internal. Well, internal is sort of related to the thermal energy, but still, we have solar energy, we have all sorts. So, when we consider what type of energy it can convert to, it can do lots of things. Okay, so things, so they often change. This often happens here. So they often change from one form to another. So an example of that could be, maybe I eat food. So what happens then? If I eat food, well then I get, that means I turn some stored energy, in the, let's say I eat some food, so I have some stored kinetic energy then in my body. Maybe I can turn that stored energy to kinetic energy by running. So maybe, this is the whole idea of how your body works. Your body works by storing up energy through, chemical forms, or you can also see it as potential. Turns out inside your body, then when you eat food, you gain some sort of stored energy, some sort of potential energy. In this case, it's probably in the form of chemical energy. And you can convert that chemical energy to kinetic energy when you're running. We have lots of different examples. I mean, we have examples of this. We have power generators. So if you actually want to generate power, well, how do you do that? You turns out you use kinetic energy. So maybe you turn some sort of wheel. You maybe have like water flowing over a wheel, or even in a nuclear power plant. The whole idea is to take this, well, in that case, nuclear energy, turn it into thermal, and then turn it into kinetic by turning a wheel still. But you turn kinetic energy to electric. I mean, this is the process. I mean, it's just a matter of counting up the energy. So I think this is really neat. We can have things that actually change. So what I wanted to show you then is a nice little animation, if I can just find it here. This is yet another awesome animation by PHET. This is the people at the University of Colorado that do these amazing, really simple, and sometimes silly looking animations, but they're really powerful. So what I'm going to do is just consider this little dude here, so this little skater, and then I'll just drop him down and we'll see what happens. Well, okay, he just goes up and down and up and down. That's a little bit boring. Let's maybe consider then something. Let's take a look a little bit more at the details here. So what if I take him then, and I'll just do, pause here. I'll put a grid here, and I want you to look at this. Let's say I have him starting at, let's say, see the little red dot right there? So this right here, I don't know if you can see that, but the little red dot that's right here, that will be the point of reference here. We're going to consider that dot. So I'm going to put him up at a height of 5. See, this is 6 meters, 4 meters. So I'm going to put him right at 5 meters here, exactly at 5 meters right there. And then I'm going to let him go. So I'm going to press play here. Watch carefully what height he reaches at the other end. So he goes down, goes back up, and he goes down and back up. Notice that he's always going down and back up to, if I just pause it here, he was going up to 5 meters again. And that's because, if you think about this, his height here, that's going to be associated with a potential energy. So you could say then that at this top part, right when he's at his very maximum height, he's not moving, so he has no kinetic energy, but he has potential energy because he's at a height of 5 meters above the ground. So in that case, you could say he has a potential energy of, well, whatever his mass is, times g times h. So, okay, fine. Now, take a look at the other end. It's conserved. Now, we talked about this, that, as long as there's no losses, well, then he'll just keep going up and down to the same height. What I want to do now, though, is take a look at a bar graph here. Let's look at right now, then, what's happening as we go along here. So let's just say we consider this right here. We're going to just, maybe I'm just going to grab him here, and I'll just pick him up again and just consider it right here. So look carefully to the right. Actually, you can't really see it, can you? Let me just move this over. There we go. Now you can see the bar graph. Okay, so let's take a look at this situation right here. So what's happening then is, do you notice how we've got different energies right here that are changing form? Let's take a look here. As right as he gets to the top, let's just see if I can stop it. So right when he's at 5 meters, look what's happening. The total energy, which means when you add up the kinetic plus potential plus thermal in that case, this plus this equals the total. And the total energy will be the same. So let's take a look then at this top part. When he's stopped, he has no kinetic energy because he's not moving. But he has maximum potential energy because he's at a maximum height. Let's take a look a little bit further now. Look what happens now. Do you notice that now at some point down below, he's got less potential energy? The reason is he's lower. But the total energy has to remain the same. That's what we called it, conservation of energy. Where did the potential energy go? Well, it went to giving him kinetic energy. In other words, making him move. And what happens at the very bottom, whoops, it's hard to sort of catch it, but at the very bottom, or very close to the bottom here, he's actually got, well, I suppose I could just put it like this right here, but then it's going to be a little bit boring because now he's got no energy. I need it to be, sort of stopping it right through his motion here, so I'll do it again maybe. I'll just press play here. I'll try to catch him right at the bottom, or very close to the bottom. The total energy is still the same, but now he's got pretty much no potential because he's at the very bottom. But look, he's got all kinetic. So do you notice? Look at these two then as it's going back and forth. It looks like they're sort of switching. See, as one goes higher, the other one goes lower. One goes lower, the other one goes higher. And this is what's happening. We have conservation of energy. So you see how the potential energy is being converted to kinetic, the kinetic is being converted to potential. So it's just like they're switching and swapping, but the total energy remains the same throughout the whole thing. Now we could take a look at his speed if we wanted. I mean, that might be interesting, I suppose. But I don't think that's really so helpful here. You can see, yes, he speeds up. He's got a maximum speed at the bottom. Actually, maybe that is important. So right down here at the very bottom, notice his speed is some maximum number. That should make sense because remember, kinetic energy is related to a speed. Kinetic energy is half mv squared. So that should work. Now what I want to show you is this. So this is kind of fun. Is what if I have this situation here? Maybe I'll just take away this, I'll take away the speed one. So I'll take the skater then and I'll just put him, now it doesn't matter of the path that I take. So what if I start him off at 4 meters high, let's say, right here. I'll let him go. Watch carefully what happens to him. So we still have him going up and over, but guess what? He can only reach a maximum height of 4. That's because you can't gain energy you didn't have in the beginning. There's no way he could finish higher than where he started. That's impossible. So this can help to explain a lot of things that go on. I mean, first of all, we were assuming, by the way, that there were no losses. We were assuming there was no friction, because it turns out that we still can have losses. So we still can have a situation right now without anything fun going on. We've just got him going back and forth to a maximum height of 5 meters and 5 meters. But watch carefully now what I can do. I can turn on friction. I'm going to have just a little bit of friction. So what this means is there's some friction because his skateboard rubs against the surface of the material here, and that means then that loses, well, you might think that some energy is lost. The kinetic and potential energy go away. Where did the energy go to? Well, it went to, let's actually take a look at it here. Let me do a little graph now. I want the graph again. Let's take a look here. So we'll take a look at him again, a situation where we're dropping him from 5. Watch carefully what happens here. We have thermal energy now, but they're still, all three of them are still adding up to the total. The thing is at the bottom right here, well then we're going to have him with, obviously maximum thermal energy. It's a little bit weird to look at. Whoops. How about I try it again, but this time when you can actually see it. I just realized that you couldn't see the chart. So I'll have it again. So this time we have him going along, and this time here we have the thermal energy. Notice the red one is going up and up and up. But still, all three of them have to add up to the same total energy. That just explains that the energy didn't just disappear, it went somewhere. The kinetic and potential weren't able to be used all the way because some of it was being given to heat, in this case friction. This is a real life situation. I mean, if you really did, drop it, from 5 meters, you really wouldn't come up exactly 5, you'd come up a little bit less. Right? And what if I have just very, very little? So real life situations are like this, where even if you have very little friction, maybe you have really good wheels, and there's not much air resistance or whatever, notice here now he won't come all the way up to 5 meters. That's because some energy was lost due to friction or air resistance or lots of other things. This can also be really fun to look at as far as doing a loop. So let's just say we have this guy right here and we want to try to consider like some sort of loop here. So we want to make someone go around in some sort of circle here. So let's just say I have something like this sort of situation here where I've got someone trying to go all the way around in a loop. You might have seen this like at a roller coaster where you're trying to go all the way around in a circle here. Doesn't really matter how I do it, but I can take another track like this. I can go like this right here. So maybe then what I can do is try to consider then this thing right here. Well, if I start my guy at some sort of very low height right here, let's say like this. Let's say I start him off right here. Notice that he can't go over the loop. That's because he didn't have a high enough height to make it. Right, we could also consider his total energy here. We can consider that here, assuming there's no friction, of course. Now what if though I extended this thing? What if I made it like this instead? So let's take him this time and drop him from here instead. Well, as I drop him, he's got enough energy now to make it all the way over. So he can actually make it all the way. Now what happens then is this. It all depends on the height of your loop. So for example, right here, if I dropped him from the top of this, try to think, could he make it to the top of this? The answer is yes, because this thing is at a lower height than this thing. So that means then if I do return skater, he'll make it now. I mean, it's not super accurate, this little thing right here, but it sort of shows you a little bit of it. So what if I had it way higher, like this right here? He'll barely be able to make it, or maybe not even, because it all depends on his starting height. So maybe I can make it like this right here. Maybe I can actually make it lower now. Now he should make it. Why is that? Because, well, it's lower than the height he was just at. So I hope that helps. You can see how, because he started with a height that was higher than the top of the loop, then he can make it. Unless you give him some speed, maybe he has his own little motor or something like that. That's a different story altogether. But it's all about how high you start. So if I wanted him to go up, some loop like this high, for example, let's say he started like this. Doesn't matter how high I can drop him from this right here, he won't make it because he doesn't have enough height. That's because he doesn't have enough total energy to make it over. Right? That's because his potential energy at the top was too low. So we can consider all sorts of situations. All I have to do is make him start off a little bit higher than it, or even the same height, and then he can make it, as long as I can sort of drop him and see what happens here. Whoops, except this didn't really work. There we go. Let's say I have him like this. There we go. This right here should make him work now because he's higher than the top of the loop. So he should be able to make it all the way over and then down. Of course, in real life, he might actually fall down. this hopefully gives you an idea of how we can work with total energy, and that's because energy is conserved.